The electric potential V for a charge Q is given by this expression. V at the potential at a point R, so let's say the charge is right here at R equal to 0, and P is a point, a distance R away. The potential at point P is given by the constant K times the strength of the charge Q divided by the distance of that point from the charge. The units of V are volts, which is equivalent to joules per coulomb, and all the other units are in SI units. So distances are measured in meters, charge in coulomb, and the constant K is on the order of 10 to the power 10 in SI units. Now let's try to visualize this potential and see what it looks like as a function of R. So if I look at the point Q here with the charge at R equal to 0, for a positive charge, the potential is huge at R equal to 0. It goes to infinity, but as R increases outward, the potential decreases as 1 over R and ultimately goes to 0 at R equal to infinity. So the potential at R going to infinity is 0, and that serves as our reference. Another way to plot this is to look at a certain radial position, go all along the circle, and you know from here that the potential is going to be constant. So these circles are equipotential surfaces or equipotential contours. And along such a contour, which I can also represent as these circles around the charge, the potential is constant. So the potential is constant along the circle, but as you step from one circle to another, the potential drops for a positive charge. So let's say this is 1000 volts. The next circle is, say, 800 volts. And the circle after that is, let's say, so the initial drop will be very fast. And this is, say, 500 volts, and so on. The electric field is the electric field is obtained from the potential by looking at two contours which are very close by and seeing how much is the change in potential as you step across these two very close by contours. So the change in the potential divided by the distance between the two contours, delta R. So let's say this contour is at R, and the contour just above that is at R plus delta R. So if I look at this ratio, that tells me what is the electric field, and I have to put a negative sign here because for a positive charge, the potential is decreasing. So delta V is negative, delta R is positive, and I want to get a positive electric field, so I have to put that negative sign there to compensate for it. And the other difference is, while the potential was a number, it was a scalar, the electric field is a vector. So that is a vector. And the direction of the electric field at any point, if you pick a point here, P, the direction of the electric field for a positive charge is outward, like radially outward. So at every point here, you can make a radius pointing outward, and that would be the direction of the electric field at any point. However, the strength of the electric field, just like the potential, will decrease with R. But it decreases faster than the potential because the electric field goes like K, the same constant we found in the potential, the strength of the charge Q divided by R square rather than R for the potential. So this is a faster power. So for the same distance, the electric field decreases faster. And R hat here tells you the direction of the electric field as pointing radially outward. Let's quickly review how the behavior of the electric field and potentials would work out for positive and negative charges. So I've made the equipotential contours. For a positive charge, these numbers would go down starting from the positive charge. So here it's, let's say, 1000 volts. The next one is 800 volts, and so on, marching down 100 volts all the way to 0 at infinity. For a negative charge, the potential in the innermost contour will be minus, let's say, 1000 volts. And then the next is less negative, minus 800 volts. And so on, minus 100 volts. And again, all the way to infinity, it would become 0. So if we had to depict a positive charge, it would grow toward the center, and a negative charge would decrease as one goes towards the center, this way. So that's V of R. This is R, that's 0, and it's decreasing, becoming more negative. The electric field for a positive charge, as we discussed, points radially outward. For a negative charge, it points radially inward. So all the arrows would point inward for a negative charge. And again, the size of the arrows, if we want to use that to show the strength, then as we move outward, the size of these arrows would get smaller and smaller. And similarly, in the positive charge case, as we move to outer circles, the size of the arrows would still point outward, but they would become smaller and smaller.